Hi, welcome to this next video on linear programming duality. In this video, we're going to talk about what happens when you take the dual of a linear program twice. So we've already seen what happens when we take the dual of a linear program of this type here on the left. So it's of general maximization type. And when you take the dual of it, you get this thing on the right. And you can see the correspondence in that the C and B flip places. The matrix A becomes transposed. Less than or equal to constraints here become variable non-negativity constraints in the dual. Free variables in the primal become matrix equality constraints in the dual. So now we're going to take the dual of this linear program on the right here, and we'll see how that linear program corresponds not only to the linear program we just took the dual of, but also to the original linear program that we started with. What's that correspondence? So in particular for this video, we are going to need to take the dual of a minimization linear program right here. So that's something that we have yet to have encountered. So that'll be new. Okay, so we're taking the dual of a minimization linear program. That's what we're going to start by figuring out how to do, and then that will allow us to see what happens when we do the dual twice, because we'll do it once and we'll get to a minimization, and then we'll take the dual of that. So here is the linear program of minimization type from above, and to practice just taking the dual of this, I'm just going to rewrite it in standard notation here. I don't mean that there's some operation that I'm performing to take us from this linear program on top to the one on bottom. I'm simply saying that I'm doing different notation. So instead of having the variables being called y's, let's call the variables x's. Instead of having the coefficients in the objective function being called b's, let's call them c's, etc. And that just gives us this linear program on bottom. You can see though that it's of exactly the same type. So we're minimizing a linear objective function subject to matrix equality constraints and variable non-negativity constraints. So that format has been preserved. Okay, and what is our goal for taking the dual of this linear program of minimization type here? Well, remember, when it was of maximization type, we wanted to put an upper bound on the objective function because the objective function was trying to grow as large as it could. Now that it's trying to grow as small as it can, since we're minimizing, we're going to try and establish a lower bound on the objective function. So that's entirely analogous reasoning, but it's just we're doing the opposite thing now. Since we're starting with a minimization problem. Okay, so how do we take the dual of linear programming of minimization type? Well, we're going to start by doing the least surprising thing that you've heard all day. We're going to take a linear combination of the matrix equality constraints. So we start with ax equals b, and we take a linear combination of them, which means that we multiply on the left by a vector y transpose of appropriate dimension. And now that we have this, what we want is for y transpose b, rather than being an upper bound, now we want it to be a lower bound. So then y transpose ax, we want that to be smaller than c transpose x. And the way that we're going to impose that is we enforce that the vector y satisfies the condition that y transpose a is less than or equal to c transpose. And if we impose that condition, then since x is non-negative, that will suffice to give us this inequality here. And then that will give us that y transpose b is a lower bound on c transpose x, which is what we want now. Okay, and so in exactly analogous fashion, instead of minimizing an upper bound, which is what we did when we took the dual of a maximization problem, now we're maximizing the lower bound. So that'll give us the tightest approximation that we can get to the optimal solution. So of the primal. So so we're maximizing this lower bound, b transpose y, and it's such that the condition that we have to impose is this condition. But I'll just write the transpose of that. It's the same thing. So a transpose y is less than or equal to c, and that linear program that is the dual of the linear program that we just started with here, which I'll call min. So by min, I'm referring to the minimization linear program that we just started with here. And so this is the dual that we get. Okay, so I've just cleaned it up. So here's the minimization problem that we started with, and here is the dual linear program that we just got. So it's this cleaned up. So maximize B transpose Y such that A transpose Y is less than or equal to C, and the Y variable components have no constraints associated to them explicitly. So they're free variables. Okay, so let's make the following observations about the correspondence of the primal and dual. And so it's very similar to how it usually works. So first, the C and B vectors, they flip places. So that's as usual. The matrix A becomes transposed in the dual. That's again as usual. We have matrix equality constraints in the primal, and that gives us free variables in the dual. And then finally, we have variable non-negativity constraints in the primal, and that gives us matrix inequality constraints in the dual. So all of that is as usual. The one thing that is not the thing that we're used to seeing is that this is less than or equal to. I wouldn't say that we are or aren't used to it. It's just that this is different than what happened when you went from a max linear program to a min linear program. Instead, when you're going from a minimization to a maximization, we have A transpose Y is less than or equal to C, and this direction of the inequality is the correct one because we want B transpose Y to be a lower bound on C transpose X. And that's in contrast to before when we did a maximization problem, we want it to be upper bound. So you can see that here with this constraint A transpose Y less than or equal to C, if you multiply both sides by the non-negative vector X here, what you'll get is that C transpose X will be larger than the thing that involves Y, and that thing turns out to be B transpose Y. So that's why we want that will make this genuinely a lower bound. Okay, so that just explains the direction of that inequality there. So let's remember that this is the correspondence going from primal to dual when you go from minimization problem to maximization problem like that. So now we are all set up to take the dual of the dual linear program. So we start with the primal linear program being of general maximization type. And we already know what happens when we take the dual. We get this linear program that we had in the beginning. And now this linear program is of the type that we just discussed how to take the dual of. So let's, using what we just discussed, let's take the dual of this and see how the dual of this linear program corresponds to the original. Okay, so what we're going to do, well, first of all, remember, when you take the dual, the C and the B flip places. In fact, when we took the dual the first time, the C and the B already flipped places. So now when we take the dual again, they're going to flip back to where they started. So actually this will be, we're going to be maximizing C transpose times V will be the choice of variable name that I'll use for this linear program now. We'll see in just a moment that it's not necessary to use this, but since it's a variable, we have free choice over the notation. So I'll use V for just this moment. Okay, so maximize C transpose V such that, okay, so we have a matrix transposed, and the matrix itself is A transpose, and that matrix is what is being transposed now. So that times, whoops, not X, V is less than or equal to B, because the C and the B are flipped. And finally, V is free variables corresponding to the fact that that we have matrix equality constraints from where we're starting here. Okay, and so now this looks pretty familiar already, but I'll make it look even more familiar now. I'm going to replace the V variable vector with X instead. So we'll have max C transpose X such that, okay, when you have a matrix A transpose, when you transpose twice, it's just the original matrix A. So A times X is less than or equal to B, and then X is a free variable, just like what we just had. So this is actually the linear program right here when we replace the V's with X's, and you can see that this linear program is in fact the exact same linear program that we started with. maximize C transpose X such that matrix inequality constraints and free variable. The primal that we started with is that maximize C transpose X such that matrix inequality constraints and free variables. So so that's a pretty interesting thing that just happened. We just took the dual twice and we got back to where we started. So our conclusion is that the dual of the dual is the primal. So yeah, I mean, I don't know, it's pretty interesting. There's it makes you think that we're actually onto something when we're discussing all these things about duality, because it's not, not just getting some random sequence of linear programs. When you take the dual, they're actually reciprocally related to each other. Okay, but what this has consequences in how we imagine linear programs at a logical and intuitive level. Namely, that from now on, what you're supposed to think about linear programs is that they come in primal-dual pairs. They come two at a time, because what happens is, maybe it's better to say what doesn't happen. What does not happen is that you have a linear program, and then you take its dual, and that'll give you another linear program, and you take the dual of that, and that'll give you a third linear program, and the dual of that will give you maybe a fourth, and you just get this chain of linear programs as you take duals. That does not happen. So what happens instead is that you take the dual of a linear program, and then you take the dual again, and you get right back to where you were. So in that sense, you have two linear programs at a time. And so these are related as a pair. So we have up top here, we have maximization linear program of general type. And for all such linear programs, when you take the dual twice, you get back to where you started. And so this linear program and its dual just once, when you take the dual, they come as a pair of linear programs. Now, we did not say that that's true when you start with a linear program that's of minimization type, but in fact it is true. And it's true for exactly analogous reasoning as for how we just explained that it's true for a maximization type. There's multiple ways to see that, but in fact, you can just use the same logic that we already have, just doing the analogous thing when you start with a minimization problem. So I won't go through the details of it because it's exactly the same thing, but it does work out that for minimization problems as well, these linear programs come in primal dual pairs, and so that accounts for all linear programs. So that means that every linear program comes as a pair of linear programs, and we consider those pairs to be primal dual pairs. So that's really the main thing to take away from this video. All linear programs come as primal dual pairs, and that's because the dual of the dual of a linear program is itself. Okay, so that's it for this video. Thanks for watching.